Reactants, products, and catalysts. Why is a catalyst not considered a reactant or a product in a chemical reaction?
Yeah, definitely. Let me pull up an image here that kind of describes what a catalyst does. Okay, so in chemistry, we often talk about reactants and products. And reactants and products are a way of describing the things that go into a chemical reaction and then what comes out of a chemical reaction. And this is one of those cases where just thinking about the words themselves, really thinking about what they mean, and those words meaning in other places can give you a hint as to which is which. So product is probably the most obvious, right? If a product is something that is produced, right, you would assume that that's sort of the end goal of something. In a chemical reaction, the products are what are produced. The reactants are then the things that would go in to the chemical reaction. So let's see, like an example of a chemical reaction might be you mix hydrochloric acid, HCl, with sodium hydroxide. When you mix those two things together, those are the reactants. So you've got them separately in bottles, throw them into the same test tube, let's say, and watch them react. And then on the other side, you would get salt, sodium chloride, and water, H2O. And those would be your products. So you have your reactants and your products. Catalysts are not reactants and products because catalysts really just sort of, in a sense, they help a reaction along. They're not little living things, but their existence, if they are around a chemical reaction, it will allow that reaction to happen faster. If we jump to my screen, I have a picture. I should probably blow it up a little bit. But this is sort of a classic graph that's shown in chemistry classes, and it sort of shows an uncatalyzed reaction in blue and a catalyzed reaction in red. And then on the left side, on the y-axis, you have the energy required to make this reaction happen, and then on the right, or on the x-axis, you have time from left to right. So as time passes, how the reaction goes. And what this is essentially saying is, if you have an uncatalyzed reaction, if you have a reaction without a catalyst, without a chemical that's going to help, the energy needed is much higher. And what this is showing is that you have to reach this level of energy before the reaction can take place. If you don't reach this level of energy described here by the peak, you cannot get the chemical reaction to happen. Sort of the downslope here represents the reaction actually occurring. This line right here is actually the activation energy line. The catalyzed reaction, shown in red, you can see requires much less activation energy, and that's because the catalyst is there helping along. And it can be something like the fact that a catalyst might have a charge, so that charge might be helping in some way. The shape of the catalyst, so if the catalyst is a complex molecule, like all of us inside of our bodies have chemicals which act as catalysts, biocatalysts, to reactions, and those are very complex proteins typically. And their shape is really what allows reactions to happen more quickly. They, in some ways, can grab onto the reactants that they need and put them together to make products. That's an oversimplification, and again, I don't want you to get the sense that chemicals are living creatures putting things together. It's because of their charges and their shapes that these things happen naturally, but it's almost as if they have that kind of agency. So anyways, really long-winded way of saying reactants go into a reaction. They're kind of like the ingredients in your recipe. Product is sort of like the thing that comes out, whatever you were baking. And then catalyst is just a chemical that can help that happen with less energy.
That was something that was really difficult for me to understand in high school until I saw an animation of a catalyst. I was like, what do you mean it helps it? How does it help?
And actually looking at animations are really great, but it is such a strange concept.
It is.
In a way. And it really is, when you talk about, I really think that it sounds like these chemicals have their own agency. Like a chemical's thinking, oh, I'm going to help this chemical get together with this chemical. But it's really just by nature of, again, its charge, its shape, how it's going to interact with other molecules, and essentially bring two closer together. And then in the case of biomolecules, it really does, the animations, like one molecule will come into the catalyst and the other molecule will come into it, and then it'll change shape and actually put them together. Yeah. Worth checking out those animations if you're trying to get an understanding of this.
Yeah, absolutely. That's what did it for me. It clicked then when I saw it. But very interesting.
I'll pull one up for later.
That stuff.
But I'll let you do a math problem. I don't want to deprive you of any.
Oh, understood. Got to share the love, right?
I saw a video of solid sodium reacting with water. It catches fire. Are there other metals that have similar reactions with water, and is that reflected in their organization on the periodic table?
Yeah, it definitely is. I will talk about that in just a moment. But let me just really quickly run through
the
enzyme
animation.
Yeah. So we could jump to my screen really fast. I just wanted to show really quickly. So, okay, so this is an enzyme.
This is so much like the
They're
I can
all
tell
like
already.
pretty much the same. This could be the one. The McGraw-Hill stuff has been there for a long time. Anyways, this is all you can just find it on the internet. It's easy to find. But an enzyme is a molecule that your body produces to help a reaction happen more quickly. So this is a catalyst to a reaction. It's a biocatalyst, so we call it an enzyme. Okay, so here's an enzyme, and then that area, the little indented area, is called the active site. That's where the reactants of the biochemical reaction will land. So you can see their shapes match up like puzzle pieces. They're called the substrate in biology or biochemistry. That's not something in strict chemistry. If you're just talking about mixing chemicals, reactants and you use a catalyst, the substrate terminology does not apply. But in biology, it does. So the substrates, which are essentially the reactants, come in. They sort of like nest into the enzyme, and then they become the product that your body wants to create, whatever that might be. So in our animation here, this is sort of happening slowly. Oh, wow. Very exciting. And then the product can then detach from the enzyme. And the enzyme can go on and continue to do this. And if we back up and kind of just look at the substrates, if I can get the thing, the substrates really, they, from their appearance, you can tell they would sort of lock together naturally. And it is true that the reaction of the substrates coming together would happen anyway, but the enzyme lowers the activation energy and allows this to happen more quickly. So that's one way to think of an enzyme. And I'll just mention also really quickly that you don't have to be combining things for this to be an enzyme. You can have a larger molecule that latches onto an enzyme, and the enzyme then breaks that up. You would still call the larger molecule the reactant, and the things that come out at the end the products. It's always the stuff that goes in that you start with that's the reactant, and the stuff that comes out, which is the product. So anyways, little wrap up of the last question. So then this new question is about sodium reacting with water. So let me pull up our handy dandy periodic table. Cool, so if we could jump to the screen really quickly. So this is ptable.com. It's a really great periodic table website that I have mentioned before on the show. So the molecules that or the elements that we're interested in here for these types of reactions are going to be our alkali metals, and to some degree our alkaline earth metals, but much more strongly our alkali metals. So the periodic table is organized in such a way that as you move from left to right on the periodic table, and this is general, the rules get more complicated as you get more in depth with it, but we'll keep it simple. So as you move from the left to the right, sort of skipping this middle area here, you add an electron to the outer orbital or electron cloud that element has. So if you haven't taken chemistry before, the basic notion is that atoms have a nucleus formed of protons and neutrons, and around the nucleus, these little tiny particles called electrons are sort of flying around in these what are called electron clouds, which just describe the space that they float around and kind of zip around in. Anyways, the outermost cloud is important in thinking about chemistry, and the periodic table allows us to know in the outer orbital how many electrons do you have. So starting from the left, you can count lithium has 1 electron in its outer orbital, beryllium has 2, boron has 3, carbon 4, nitrogen 5, oxygen 6, fluorine 7, and then neon 8. And 8 is a full orbital. And again, I'm glossing over some finer details, but generally this is true. Okay, so back to the question. Alkali metals, so all alkali metals are in this left-hand column, meaning they all have just a single electron in their outer electron cloud or outer orbital. They would really like to get rid of that extra electron for reasons of stability. When they have the electron, they're charged neutrally. But when they lose the electron, they become positively charged, and they would really like to lose that electron. And if you take a block of, let's say lithium, or what is it, sodium in this case, you take a block of sodium, and sodium is a metal, It's not a metal like we tend to think of metal like iron, but you could get a block of sodium. You'd have to order it specialty, and it's very dangerous because it could even react with oxygen. And if you were like to throw it into water, it really does look like it sets the water on fire. And effectively what's happening is all of the sodium gets in the water, and water is polar, and the sodium will just instantly give up that electron that it has. Polar means that the water has a positive and a negative side. So the electrons will be given up, and the sodium will become positive. And sodium is very positive at that point, and it would really like to latch onto something else. And so it will actually break up water. And so water, which is H2O, will be broken up, and H will be ripped off of the water molecule. It'll combine with another H to form hydrogen gas, and will gas off. And the OH that's left over, a compound called hydroxide, will latch onto whatever the alkali metal was, in this case sodium. So you end up with a compound called sodium hydroxide, or you end up with sodium and hydroxide ions in the solution. But it's essentially the energy of that really positive alkali metal ripping apart the water molecule and joining the hydroxide piece that releases so much energy that it is a fire, essentially, is what you get. You get the burning of water, which is what this is. And so really this is reflected by the organization on the periodic table. The most reactive is lithium. Lithium is the least electronegative element. But then as you move down the scale, all of these guys, sodium, potassium, rubidium, cesium, and francium, would all react really strongly with water.
All right. When learning about the Aurora, oh gosh, I don't know how to pronounce that. Borealis, also known as northern lights, I found out they are caused in part by the Earth's magnetic field and atmosphere. But what is the interaction that actually causes visible light?
Yeah. Do you know what Aurora Borealis means? It means northern lights. So Aurora means light.
I was going to guess that, actually.
And then Borealis means northern, or boreal, right? You sometimes hear about boreal forests, northern forests. But yeah, anyways, sorry. So the Aurora Borealis is fascinating, and probably everybody has seen a picture of the northern lights in their lifetime. Hopefully everybody has. They're gorgeous. I've never actually seen them.
I went to Alaska in the summer, and people asked me,
Did you get to see
Did
them?
you get to see the northern lights?
And did you?
No, I went in the summer.
Oh, you went? Sure. So,
No sunset even.
And that really is the thing, right? So you need the dark to be able to see the northern lights because they're just dimmer than the light of the sun. So the way that this happens is Earth does have a magnetic field. Let's just really quickly talk about that and why. If we could jump to my screen really quickly. So Earth has a magnetic field that generates because of its plates and its mantle and its core. And essentially the idea is that the Earth is composed of a lot of nickel and iron inside of itself. Out here on the surface, it's composed of lots of silica and other things, but it's very iron and nickel rich in the core of the Earth. And iron and nickel are two metals, or they're elements that are metals that are able to generate magnetism and electricity. And essentially what you have is, I've got, I think, another image I tried to pull up here. So this is an image of convection current. So the core of the Earth is the hottest, densest part of the Earth, and as it heats the stuff around it, the mantle is liquid or approaching liquid, and so it has currents inside of it, and the currents of this like molten iron and nickel mixture, as they move and sort of swim through the mantle in these, as described by these little circles with arrows here, they move continents apart and bring them together, which is super relevant for geology. But in this case, what we're interested in is that they actually move electrons around as they're doing this. The individual iron and nickel atoms will actually pull and push electrons around inside the core, and it generates some fairly consistent fields, electromagnetic fields. And so then what you get is the sun's rays, as they shine down on Earth or toward Earth, there are electrons contained in those rays, and they get pulled by the pole, the northern pole of the Earth. And so you can see here in the diagram we have electrons and ions being pulled, negatively charged ions being pulled toward the northern pole of the Earth. And so as these electrons and ions come toward the northern pole of the Earth, they start knocking into the gases in our atmosphere. And the most common gases in our atmosphere, so the most common gas in our atmosphere is not oxygen, but nitrogen. Nitrogen is like 78% of the atmosphere, and it's in the form of N2, and it's kind of inert, doesn't really do anything. And there's about 20-something% oxygen, and then there's smaller amounts of things like carbon dioxide and water vapor. But nitrogen, when it gets knocked into by these electrons and these ions, what will happen is those electrons will excite, sort of add energy to the gas molecules as they're floating around. And the electrons of those gas molecules will get excited and will do what we call jumping energy levels. And so they'll get excited and they'll move further away from the nucleus of the atom, and they'll have more energy. And then they'll lose that energy and they'll jump back to that original position. And in that loss of energy, the electron will give off a photon, which is an energy packet seen as light. So, and this is a really cool phenomenon that happens not just from the Northern Lights, but I used to be a park ranger in Carlsbad Caverns in New Mexico, and we had the cave is formed out of limestone in Carlsbad, and there was this one particular statue where we used to do this thing. It looked kind of like a crocodile, and we had gigantic lights. It's a cave. It's very dark in there. So we had these gigantic flashlights we carried around as rangers. And if you shined the flashlight into the eye of the alligator, I mean, you could have done this to any piece of rock in the cave. But if you did it to the eye of the alligator, the photons emitted from the beam from the flashlight would actually excite the electrons of the limestone atoms. And they would jump energy levels. And then if you pulled your flashlight away, those electrons would jump back to their original energy levels, give off photons themselves, and that would give off this greenish light. And so the eye of this rock alligator would glow green in the dark. It was really a cool little thing. But it's essentially the same process. And then, there's different colors in the Northern Lights, and that is because of the different chemicals. So nitrogen, I think, is seen as, what was it? Nitrogen is seen as red, and oxygen is seen as green, I believe. I can't remember. I looked it up. But in any case, that's the gist of why this happens. It's that exciting of electrons to a higher energy state, and that can happen in lots of different ways. And then when those electrons jump back to their normal energy states, they give off a photon, and that is what we see as the Aurora Borealis.
That is so cool.
Yeah, it's really interesting.
That was really cool.
Interesting stuff.
Wow.
I know the nervous system runs through our whole bodies, but exactly what part of that is considered the central nervous system?
So that'd be the brain and the spinal cord.
Yeah.
Done, your turn. Just kidding. Just kidding. I'm just joking. I'll talk about it for a minute.
Wow. Not fair.
So the central nervous system, let me pull up a diagram of it, and we'll just talk a little about what the nervous system does and why we call it the nervous system, etc., etc., etc. If Nate were here, I might have done that. But, okay, we'll pull up this really generic-looking human. Just white male, average age. Okay, if we could jump to my screen really quickly, please. So this is just a really simple diagram that shows the brain and the spinal cord. Spinal cord is just like a really thick braiding of nerves that comes off of the brain and acts as sort of the central wire that all other neurons are connected to. And I think it is apt to describe nerves like wires. They're obviously not exactly like wires that we use in machines, but they perform very similarly, and really the way that our nerves work is through electricity. Our bodies in general function through electricity, but our nerves in particular through what's called action potential. Essentially, neurons can send messages by pushing positively charged ions across a medium, and then as those ions move back across the medium, they'll send electrons moving, and that can essentially create an electrical pulse. In any case, the remainder of the nervous system extends through the body. You can kind of see from this diagram all these different little fibrils coming off of the spinal cord, and those would, of course, extend to all different parts of the body, giving us sensations like the sense of touch and temperature and pressure and all of that information, calculated instantly for us thanks to the good old brain. Sorry, I talked about that for as long as I could. That was as good as I could do.
Still interesting, though. I like it.
Mm-hmm.